Good day. Welcome to Phoenix Tutorials. In this video, we'll be talking about integrals. And in this case, we have the integral of a rational function. So the rational function, because we have a polynomial being divided by another polynomial. So in this case, we have a first degree polynomial being divided by a second degree polynomial. And just about these rational functions, you actually have to sketch them if you do AP Maths, and you'd actually encounter something called a vertical asymptote, horizontal asymptote, and an oblique asymptote. So vertical, horizontal, oblique asymptotes, those are all terms that you'd have to discuss when you have to draw those types of functions. And an asymptote, obviously, it's where you have a value for x that's undefined, and it actually shoots up to infinity in a sense, but that's what an asymptote is. And in this case, we have 1 plus x over 1 plus x squared. We have a first degree polynomial over a second degree polynomial. So we have x to the power of 1. So our first step would be to separate the fraction. So we have a fraction, and we know we have to add two fractions. The denominators have to be the same. So some basic maths rules. I have to add those two. Then my denominators would have to be the same. So in this case, we are reversing that process by saying that we'll split this sum up into 1 over 1 plus x squared plus x over 1 plus x squared. So looking at these two terms, I have, once again, two rational functions. And in the other rational function, I have a first degree polynomial being divided by a second degree polynomial. Okay, now we can apply our integration operator. In this case, we are using the fact that an integral is a linear operator, so I can apply it everywhere. And in this case, we can treat the integrals as two separate integrals. And for the first integral, we have an antiderivative. So it's antiderivative of 1 over 1 plus x squared is arctan x. So antiderivative meaning that you have to study your table of derivatives. For the second integral, we can use u-substitution over here because we have a first degree polynomial being divided by a second degree polynomial. So something like I have an n over there and I have n less than 1. I can use substitution because of derivatives. So the condition here is the function on my numerator has to be 1 degree less. So in this case, we have x to the power of 1 and 2. So we have n is 2. That means n minus 1 is 1. So whenever you have a structure of that form, you can use u-substitution. So something like 1 plus x to the 4, that would satisfy the condition for u-substitution. And you asked to integrate that, you definitely use substitution because it fits the description for u-substitution. And why are we using the exponents over here? That's because we have to use the power rule when we differentiate using the substitution rule. So how does that work? So what happens here is we'll allow our function in the denominator to be our u. So we'll say u is our function in our denominator, and then we'll take the derivative of that function. This is a normal derivative. We'll say du over dx is 2x, and we multiply across by the dx. So we can see over here we had a dx, And then what happened there was we multiplied across by dx in order to get rid of it. And then it's on the other side. So multiply both sides by dx. And this will be useful because we'll substitute this into our integral. So now we have a dx over here. So that dx and that dx, those two are exactly the same. So I can say dx is du over 2x. And then that's why what they mean when say you substitute, because you're just gonna plug back in um plug back in, and then you will simplify your integral. Let's see how they carry on in the notes. So over here, they might use a trick, but that's fine. So what they do here is let's bring it back. So they have the u over here. This is our function u. 1 plus x squared was u. And then we had dx. dx was du. Had du. And then we divided that du by a 2x. And then at the top, we still have our x. So that's why we call it u-substitution, because you eliminate the x by substituting it with a different variable. So those two x's will cancel. Then we're left with the final neat integral. So it's a half. Then we have the integral. Then we have du over u. So once again, that brings me back to my table of antiderivatives. So what do I mean by that? What I mean by that is you have a table where you study your antiderivatives. So you'll memorize the fact that the antiderivative of 1 over 1 plus x squared is the inverse tangent of x, and the antiderivative of 1 over u, or you could say the integral of 1 over u, that's ln u. And in this case, ln u, the natural log, is 1 plus x squared. So that would be the final answer. So we are summing up our two answers because we had two different integrals. So now let's summarize. So we have our problem by Phoenix Tutorials, our first YouTube video, and we have a rational function. And we spoke about rational functions having asymptotes. It can have a vertical asymptote, an oblique asymptote, as well as a horizontal asymptote. And if you do something like AP Maths in grade 12 IEB, you would encounter these functions and you have to sketch them. But in this case, we are taking the integral. So we have to split the rational function up. As you would add two fractions, you have two different integrals. In this case, we know the antiderivative is inverse tan of x. And in this case, we have a polynomial of degree 1 and a polynomial of degree 2. So we know that we're going to use substitution method by leveraging the power rule when we differentiate polynomial functions. So we get u is 1 plus x squared. That's the highest degree. We get our derivative and we plug in, as I just displayed in this video. And then we have our final function, which was a half. And then we have du over u. And we already know that if we take the antiderivative or integral of that function, we'll get a natural log. And then we add our two final answers up, and we add constant of integration, because integration in this case is indefinite. So we are assuming that we are giving you an answer that's actually an infinite number of functions where c can be anything, as opposed to a definite integral where we are finding the area of a function beneath the curve and we have bounds for our integral. Thank you very much, and we'll